Let's finish our introduction to significance tests. We're going to talk about some error today. Type 1 and type 2 error is called. Sometimes when we draw a conclusion from these significance tests, our conclusion is going to be wrong. We hope that we're right, but sometimes it's not. And there are two types of mistakes that can be made, and we saw those in the previous video. We can reject the null hypothesis when it's actually true, or we can fail to reject a false null hypothesis. Failing to reject the null, rejecting the null when it's true is called a type 1 error. Failing to reject a false null hypothesis is called a type 2 error. And these can be difficult to keep straight. I don't really have a nice way of remembering it. It's just something you have to remember. When we're rejecting H0, when we're rejecting the null and it's true, it's type 1. When we don't reject the null when it's false, we're committing type 2. So here's a two-way table to visualize this for those of you that are visual learners. One of these two things should help you to remember. It's if you're allowed some notes to keep track of this, that would be an excellent thing to make sure you have written down. What's type 1, what's type 2? So an example, we're talking perfect potatoes. So pause the video, read this example. Okay, so we have a null hypothesis saying that the proportion is equal to 0.08. And our alternative hypothesis, the thing we're trying to show, is that more than 8% have blemishes. So P is greater than 0.08 is HA. Describe type 1 and type 2. Okay, so type 1 is when H0 is true, but we're rejecting it. So type 1 would occur when the producer concludes that the proportion of potatoes is greater than 0.08 when the actual is 0.08 or less. The consequence of this in the context of the problem would be that the potato chip producer sends a lot of acceptable potatoes away, and that might result in lost revenue. A type 2 error occurs if the producer doesn't send the truck away when there are more than 8% of potatoes that are bad. The consequence is that we make a bunch of potato chips that are ugly potato chips. They're blemished, and the customers could be upset about this. So type 1, type 2, make sure you see how these fit in with the null hypothesis and alternate hypotheses. So error. We can assess the performance of the significance test by looking at the probabilities of the two types of error. And statistical inference is based on what would happen if I did this many times. It's not a one-time deal. Remember, that's what confidence interval was. If we repeated this process multiple times, repeatedly, we would expect this percentage to be of the true population to be within our interval. So same idea here. We're going to do this many times. So we're still looking at our potato example. We're testing the null and alternative hypotheses again, where P is the actual proportion. Suppose that the producer decides to carry out this test on a random sample of 500 potatoes using a 5% significance level. That is alpha equals 0.05. If we assume that the null hypothesis is true, the sampling distribution of P hat will have an approximately normal shape because NP and 1 minus P are both greater than or equal to 10. It will have a center where the mean of the P hats will be equal to our proportion, and the spread we can calculate with our standard deviation. And we should be making sure that our condition for independence holds true also. Have we met the 10% condition? Yeah, there's more than 5,000 potatoes in the world. So our standard deviation is 0.0121. So we're normal, we've got a center, a mean of 0.08, and a standard deviation of 0.0121. So what we get is a normal distribution that looks like this. The sampling distribution of p hat if the null hypothesis is true. So notice the null hypothesis is right here in the middle. If we calculate the inverse normal distribution with a mean of 0.08 and a standard deviation of 0.0121, we get 0.0999. That value is the cutoff for where we reject or fail to reject the null hypothesis. Our 5% significance level is up here. If we get a p hat, if we collect a sample and p hat is up here, let's say we get 0.10, we would reject the null hypothesis. It's too different from what we're claiming to help us fail to reject that. If we get a p hat down here, we would fail to reject the null hypothesis. In other words, we would be accepting the alternative hypothesis. So let's put this in context of error, type 1, type 2. If we reject the null hypothesis, but the null hypothesis was really true, that means that p hat is up here. That means this probability is the probability of type 1 error. These p hats would cause us to reject the null hypothesis. But if it's true, this percentage is our type 1 error. This is the probability of getting a type 1 error. It is the same as the significance level. So put that into writing. The shaded area is 0.5%. The sample proportion values to the right of the green line that we're getting from doing an inverse normal calculation, 0.0999, will cause us to reject H0 even if H0 is true. This will happen in 5% of all samples. That is, probability of making a type 1 error is 0.05. And again, the type 1 error is simply the significance level of the test. The significance level alpha of any fixed level test is the probability of a type 1 error. That is, alpha is the probability the test will reject the null hypothesis even when H0, even when the null hypothesis is in fact true. When you're choosing your significance level, you need to be conscious that this is what you're actually choosing. What's the probability that I'm rejecting the null even when I shouldn't? What about type 2? A significance test will make a type 2 error when it's failing to reject the null that's really false. There's a lot of values of the parameter that satisfy an alternate hypothesis. So we're going to look at one value at a time when we're looking at type 2 error. We can calculate the probability that a test does reject the null when an alternative is true. This probability is called the power against that specific alternative. So the power of a test is the probability that the test will reject the null at a chosen significance level alpha when the specified alternative value is true. So what does that look like? Well, we're going to go back to our potato chips. We've got our null hypothesis, our alternative hypothesis still. We've got a random sample of 500 potatoes. We're wondering, will there be enough power to detect a shipment that has 11% blemished potatoes? In that case, what we're looking at is a type 2 error where we fail to reject the null hypothesis when the true proportion is 0.11. So that's our specific value for P. So this was the picture we had. Here's our probability of a type 1. Earlier, we decided to reject the null hypothesis at a 5% significance level if our sample yielded a sample proportion to the right of the green line. Our cutoff value was a sample proportion of 0.0999. But what if the true proportion wasn't 0.08? What if that true proportion was 0.11? Well, now we get this picture. And let me look at this a little bit different. Let me look at it with both bell curves together. So what we have was this picture, but now we're going to change this and frame it in the sense that the true proportion isn't 0.08, but it's really 0.11. Notice that the bell curve is now centered at 0.11, but our cutoff value of 0.0999 is still here. So we're wondering, what's the probability that we're greater than that now? So what's the probability that we're going to reject? So now this is a different picture. We now have a different bell curve. We're doing a different calculation, but it's related to the original. All we're doing is changing the center of our bell curve. All we're doing is, instead of a mean of 0.08, we're shifting it to having this mean of 0.11. Our cutoff for rejecting the null hypothesis is still the same value. So using this, using our standard deviation, using our probabilities that we saw before, now we have 0.7517. And let's go back to the presentation here. So we rejected the null hypothesis at a significance level of 0.05 if our sample yields a proportion, a p-hat, greater than this 0.0999. So we'd be correctly rejecting the shipment about 75% of the time if our true proportion was 0.11. The power of a test against any alternative, so the power of this test against an alternative being 0.11, will be 1 minus the probability of a type 2 error. So the probability of a type 2 error is that we don't reject the null hypothesis when it is false. That's this part down here. That is our 0.2483. So about 25% of the time, we are not rejecting the null hypothesis when it's false, for the specific instance of the true proportion being 0.11. So how large of a sample should we take when we plan to carry out a significance test? That answer depends on what alternate values of the parameter are important to detect. Here are the questions that we have to answer. Significance level. How much protection do we want against the type 1 error? That is, getting a significant result from our sample when H sub 0 is really true. The practical importance. How large a difference between the hypothesized parameter and the actual parameter is important. And finally, power. How confident do we want to be that our study will detect a difference of the size we think is important? So, a summary of the influences on the question, how many do I need? If you insist on a smaller significance level, such as 1% versus 5%, you have to take a larger sample. A smaller significance level requires stronger evidence to reject the null hypothesis. If you insist on a higher power, you'll need a larger sample. Higher power gives a better chance of detecting a difference when it's really there, but better results, larger samples. And at any significance level or desired power, detecting a small difference requires a larger sample than detecting a large difference. Detecting a large difference from it, if we want to detect a result that's really, really different from it, that should be shown using a smaller sample size. But if I want to be real specific, if I want to know how different something is that's on a real small scale, we need lots of data to figure that out, to get a good, accurate depiction of what's happening. So here we go. We are finally done with the basics. Here is a summary. Again, I really strongly urge you to have really good notes for this, to really be clear in your definitions, and probably watch this multiple times. In the next couple sections, we'll be looking at how we do these significant tests, actually how we do them for proportions and then for means.